Hello, today is the 10th. Percy.
Here.
Urani, not here. Kilcrease, not here. Lucky is here. Luna, don't see Luna. Messias, not here. McKinnon, not here. Morris is here. Powers is here. Renfro, not here. Salvador, and Spivey is here. Okay. So we're going to continue our discussion of equilibrium. And let me get to the PowerPoint here. So what we're going to look at is how do we determine the equilibrium constant based on the initial amounts of reactants. And let's say we start off with a certain amount of reactants and we know what the reaction is in terms of the equation. We can determine the equilibrium concentrations based on the stoichiometry. And then after that, we can determine the equilibrium constant. All right, so as stated here, when you have the initial amounts of one or more species and the equilibrium amounts of one or more species, so let's say those are given, then we can determine the amounts of the remaining species using the stoichiometry of the equation. All right, so the approach that is taken, usually when it comes to solving problems of this type, is that we start off with the concentration of the substances that are present before equilibrium, in other words, initially, and then we determine the changes in these concentrations that occur when the system reaches equilibrium. And then based on that, we'll have all the equilibrium concentrations and we can plug those values into the equilibrium expression. And that's how we determine the Kc, all right? So we call this approach, or the table that is generated by this approach, we call it an ICE table. ICE meaning initial, change, and equilibrium, all right? So we're gonna see a couple of examples of this, starting with this one right here. Whoops, sorry. So we're gonna start with this example right here. And in this example, it says you have a 10-liter vessel at 1000 Kelvin, and the amount of SO2 is given. That is the initial amount, I should say. They also gave the initial amount of O2, and then they said that they react to form 0.162 moles of SO3 at equilibrium. So the question is asking, what is the Kc for the reaction? And it gives you the equation here, right? So we have some diagrams here to help us visualize what's going on. Here we have the initial amount of SO2 and O2. There's no SO3 to begin with. And then when the system, so that's the initial state. And then, just keep that. And then when the system moves to equilibrium, we have, according to the question, we have at equilibrium 0.162 moles of SO3. So the question is, we need to determine the Kc value. In order for us to do that, we need to determine the amount of SO2 and O2, all right? So this is how the ICE table works. I'm going to construct a table right underneath the equation here. So here, I'm going to put the initial amounts of everything before equilibrium. So before equilibrium, we had 0.250 moles of SO2. We had 0.200 moles of O2, and we had no SO3, right? Now at equilibrium, according to the question, the only thing that is given to us is the amount of SO3. Let me just draw some lines here to make things a bit more clearer. So at equilibrium, we're given that we have 0.162 moles of SO3, right? So as you can see here from the question signs here, what we need to find are the equilibrium amounts of SO2, which we can write down here, and the equilibrium amount of O2 that is going to be written down here. So the question now becomes, how do we find out those values? Well, it's based on the stoichiometry of this equation here. Firstly, we can see that as far as the SO3 is concerned, the change in the amount of SO3 would be plus 0.162 moles, right? Because we're going from 0 moles of SO3 to 0.162 moles, right? So therefore, the change in the amount of SO3 would be plus 0.162 moles, right? Now, based on the stoichiometry of this equation, we can see that for every 2 moles of SO2 that reacts, there are 2 moles of SO3 that is produced. So therefore, that tells us that the change as far as the SO2 is concerned, is minus 0.162 moles, right? Because of the 1-to-1 ratio or 2-to-2 ratio between the SO2 and the SO3. So what about the O2? Well, based on the stoichiometry of the equation, for every 2 moles of SO3 that is produced, 1 mole of SO2 will react. So therefore, what that tells us is that the amount of change as far as the SO2 is concerned would be minus half of 0.162 moles. All right? So now that we have the changes, we can calculate the amount of both SO2 and O2 at equilibrium. So together. So as far as the SO2 is concerned, that would be 0.250 minus 0.162. And according to my calculations, this works out to be 0.088 moles. And then as far as the O2 is concerned, that would be 0.2 minus half of 0.162. And according to my calculation, this means that the amount of O2 remaining would be 0.119 moles. And we already have the equilibrium amount of SO3. So now we have the equilibrium values in moles for all these components in the mixture. So what we need to do next is find the concentration of each of them. So the concentration of SO2 would be equal to 0.088 moles divided by the volume. What's the volume? Well, according to the question, the volume of the vessel is 10.0 liters. So 10.0 liters, and that would be equal to 8.8 times 10 to the minus 3 moles, or I should say M, moles per liter. And then the concentration of O2 will be equal to 0.119 moles divided by the volume, which again is 10.0 liters because they're all in the same container. So that would be 0.0119 mole, I keep saying moles, M. And then for the concentration of SO3, that would be equal to 0.162 moles divided by 10.0 liters. So that's going to be equal to 0.0162 M, right? So now that we have the molarities at equilibrium for all the different components in the system, we can calculate Kc. And based on the balanced equation, the Kc expression would be concentration of SO3 squared divided by the concentration of SO2 squared times the concentration of O2, and then we plug the numbers in. So for SO3, that would be 0.162 squared divided by 8.8 times 10 to the minus 3 multiplied by 0.0119, and then we work these out. So 0.10. Very important, this should be squared. All right, the concentration of SO2. Okay, so let me do this now. Number crunching, 0.162 squared divided by, 8.8 times 10 to the minus 3 squared divided by 0.0119. And wrote it off to 3 sig figs. According to my calculations, this works out to be equal to 2.85 times 10 to the 4. All right, let me do this again just to make sure. 0.162 squared divided by 3. That was 0.019. Yeah, that's all different. I got 2.51 times 10 to the 2. Let me do this again.
Did you square the 8.8 times 10 to the negative 3?
All right, let me try it again. Squared divided by 8.8 times 10 to the minus 3 squared. You're probably right. I probably didn't square the 8 point. Okay. Okay, I got 2.85 times 10 to the 4.
Yeah, that's.
Okay, all right, okay, I'll go with that. I was right the first time, I don't know why I was doubting myself. Okay, so that's basically how you approach a problem of this type, all right? Any questions about this? Any question? Any questions out there in Zoom? Okay, so let me continue. So we're gonna look at some other types of problems where, let's say you're given the KC and you're asked to determine the amount of substances or the concentrations of the different substances in equilibrium, all right? So this would be kind of like the reverse of what we just did. Now, let me just say, so that you're forewarned, that this is actually more challenging than what we just did, because it will, in some cases, it will involve algebra, which may include solving a quadratic equation, all right? And I'm quite sure you have had that experience in math, so there's no need for me to teach you about quadratic equations. So let me just start with what is being discussed here. So it says here that let's say you're starting with initial reactants and no products, and you have knowledge of what the equilibrium constant is, then you can use an ice table, just like we did before. But this time we have to introduce an unknown X, which represents the change in the concentrations of one of the reactants. And then after you have determined what X is, which would involve writing down the equilibrium expression and doing some algebraic manipulations. Once you find out what X is, then basically you can use that X value to determine the equilibrium concentrations of the different components in the system. So the best way to learn about how to do this is, of course, to go directly into an example. And here is one such example. So it says, it gives you the equation, it gives you the Kc value, and the question says, if we start with 0.500 moles of iodine and 0.500 moles of H2 in a 5.25 liter vessel at 698 kelvins, how many moles of each gas will be present at equilibrium? All right, so that's the question. Now, first thing I would do is write down the Kc expression. Okay, what's going on here? Let me write it up here. Kc, based on this equation, would be equal to the concentration of Hi squared divided by the concentration of H2 times the concentration of I2. And that would be equal to 54.3. All right, so I'm going to start out with that, right? I'm going to rewrite the equation down here, and I'm going to set up an ice table like what we did before, but there will be some differences because of the nature of this question. So initially, before we do that, I'm sorry, there's something I should have mentioned. So because we're dealing with concentration terms, let me erase this here. I'm sorry about that. What we need to do is determine the initial concentrations of whatever is present initially, all right? It turns out, and this allows us to kill two birds with one stone, the number of moles of iodine and H2 would be the same, right? So we can say that the concentration of I2 would be equal to the concentration of H2, and this is initially, so let me put initially right here. Initially, right, the concentration of I2 would be equal to the concentration of H2, which would be equal to 0.500 moles divided by 5.25 liters. So we have to do that calculation first, right? 0.5 divided by 5.25. And according to my calculation, this works out to be equal to 0.0952 M, all right? So now I'm going to get into my ice table, H2 plus I2 to give HI, 2HI. And initially, the concentrations of both H2 and I2 would be 0.0952, 0.0952. And initially, the concentration of HI would be 0, okay? So this is where the X factor comes in, right? We don't know how much of the H2 or I2 reacted, but we're just gonna say let X equal to the amount of H2 reacting, all right? So as reacting. So as far as the changes are concerned, the amount of H2 reactant will be minus X. The amount of I2, because it's a 1-to-1 ratio, mole-wise, of I2 reactant will be minus X. And as far as the HI is concerned, it's a 2-to-1 mole ratio between the HI that is produced and the H2 that is reacting. So therefore, I'm going to put plus 2X here. Of course, it's plus because HI is being produced. So at equilibrium, we can write down expressions for each of these terms by simply adding this line to this line. So basically, for the H2, it is 0.0952 minus X. Here, you're going to have 0.0952 minus X, and here you're going to have 2X, right? So these are the equilibrium expressions for all the substances involved in the reaction. And what we can do from here is that we can plug each of these terms into this equation right here, the Kc expression right here, right? So because I'm going to need space, I'm going to erase some of this here. I'm going to erase this top part here. Sorry about that. So what I'm going to do up here is plug each of these terms into the Kc expression here, right? So that would mean that Kc, which is 54.3, would be equal to the concentration of Hi squared, which would be 2x squared, divided by the concentration of H2, which is 0.0952 minus x, multiplied by the same thing. So guess what? I'm just going to square this, all right? Because it's 0.0952 times minus x times the same thing, 0.0952 minus x, right? So basically, it's all algebra from here, right? Basically, your aim is to solve for x. So what I would do is, because you have this part here squared and this part here squared, if you find the square root of that side, you have to do the same thing for this side, right? So let me see what the square root of 54.3 is. 54.3, find the square root of that. So that would be equal to 7.36. And that would be equal to 2x over 0.0952 minus x. And then we have to, I don't remember the term that you use in math or algebra. It's been a while since I've done a math course. Oops, I erased something accidentally. So this is 0.0952. Okay, so basically what I'm going to do is I'm going to cross multiply. I don't know if that's the right term that I use nowadays. You're going to end up with 2x is equal to 7.36 times 0.0952 minus x. And then I'm going to, what's the word? Distribute the 7.36 among what you have within the parentheses. So 7.36 times 0.0952. So when I did that calculation, I got 0.701 minus 7.36x. That would be equal to 2x. And then I'll put like terms, which means that what I'm going to do is add 7.36x to both sides. So when I add it to that side, I get 9.36x. And this will cancel out with this. And that'll be equal to 0.701, which means that x will be equal to 0.701 over 9.36. So let's see what that gives. 0.701 divided by 9.36. And according to my calculations, this works out to be equal to 0.0749. Okay, so what does that mean? Now, remember, what the question is asking for is how many moles of each gas will be present, right? So what I would do is, I need some more space again. Let me erase up here. Now, as I recall, based on what the table I had before, I determined that at equilibrium, the concentration of H2 is equal to the concentration of I2, which would be equal to, what was it, 0.0952 and 52 minus X, right? X is this that we just calculated, 0.0749, right? So what does that give? 0.0952 minus 0.0749. So I got 0.0203 M, right? And the concentration of HI is equal to, if I remember correctly, it was 2x, right? From the table. So 2x, which is equal to 2 times 0.0749. So let's see what that gives. 0.0749, 0.0749 times 2. So I got 0.1498. Well, rounded off to 3 6 that would be 0.150 M, right? So those are the concentrations at equilibrium, but the question is not asking for the concentrations at equilibrium. The question is asking for the number of moles at equilibrium. So how would you find the number of moles at equilibrium? We have the concentration. What do you need? If you have the concentration of something, what do you need to find the moles? Or more specifically, if you have the molarity of something, what do you need to find the moles? Exactly, the volume in liters. So the moles of H2 would be equal to 0.0203 M multiplied by the volume in liters, which is 10.0 liters, and that would equal to 0.203 moles. And the moles, and this also, by the way, this is also equal to the moles of I2, right? Because remember, we said from earlier, the moles of I2 and the moles of H2 in the final concentration will be the same. And then the moles of HI would be, again, the molarity, 0.150 moles, or M, times 10.0 liters, which would be equal to 1.50 moles. So,
Yeah, where did you get the 10 liters from? Because isn't it 5.25?
oh, sorry, you're right. Where did I get a 10 from? I don't know. 5.25. I'm sorry about that. Yeah, you're right. I think I was thinking of previous example. Yeah, 5.25. My bad. So 5.25 here, that means that answer, both answers are wrong. 5.25. So let me just erase these. Okay, so 0.0203 times 5.25. So here I got 1.107. So this is 0.107 moles, and here I got 0.736, so 0.788 moles. So these are the answers here and here. Okay, so that's basically how that is done. All right? Any questions about this? Any questions? Okay, I think this is the last. Oh, actually one more, okay. So any question about this? Any questions about this example? No questions? Okay, the next example says carbon monoxide and chlorine react to form a compound known as phosgene, and it gives you the equation and it gives you the Kc expression. And the question says how much of each substance in moles will there be at equilibrium in a reaction mixture that initially has 0.0100 moles of carbon monoxide, the same amount of chlorine, and 0.100 moles of COCl2 in a 10-liter flask. Okay, so I think I'm gonna need more space than what's provided here. So let me use Word. Let me come back to this and let me copy this here. Okay, now I can. Okay, so that's a question. Let me make this a little bit smaller. Okay, so the question gives you the equation. Somehow when I copied and pasted it, I lost the arrows here. Okay, so they gave you the equation, they gave you the Kc value, and it says how much of each substance in moles would there be at equilibrium in a reaction mixture that initially had these amounts, right? For the carbon monoxide, the chlorine, and the phosgene in a 10-liter vessel, right? So I'm just going to rewrite the equation here. But before I write the equation, the first thing I would do, or let me ask you this. Let me hear what your idea is. What do you think your first approach would be in answering this question? Very first thing, before anything else. They gave you the equation and they gave you the amounts of each substance before equilibrium in terms of moles, right? And the question is asking how many moles of each of them will be there at equilibrium, right? So what would be your first step?
Divide the 0.0.
I'm sorry?
Would he divide it like he did with the other one?
You would do a division to find something.
Like Kc equals the concentration of.
Well, that is true for Kc, but here's the thing. Okay, let me write down what I think you're saying. Kc would be equal to the concentration of COCl2 divided by the concentration of CO times the concentration of Cl2, right? Okay, but remember now, these are equilibrium values that when you plug into this equation, you get Kc. These values are not equilibrium values. These values are values before equilibrium, right? And just to give you a little hint, I don't know if this would work in terms of helping you towards the answer. If you remember the last time you were here, we talked about comparing QC to Kc in order to predict which direction the reaction is going to shift. Remember that? We talked about QC. QC is basically the same equation as Kc, excepting that those terms are not necessarily equilibrium terms, right? So if you remember, I said that if QC is less than Kc, the reaction is going to shift to the right. But if QC is greater than Kc, then the reaction is going to shift to the left in order to achieve equilibrium. All right? So that's the first thing we need to figure out in this particular question. Given the concentrations that we're given, well, not the concentrations, I'm sorry. Given the moles that we're given, right? We have to make a prediction as to which direction the reaction is going to shift. In other words, we need to find out what QC is, right? So QC in terms of these values right here. So the first thing I would do is find the concentration initially of carbon monoxide. And by the way, since carbon monoxide and chlorine have the same mole value, their concentrations are going to be the same. So again, we can kill two birds with one stone. So we're going to divide 0.0100 moles of chlorine or carbon monoxide divided by the volume, which is 10.0 liters. And this would give 1.00 times 10 to the minus 3 m, right? And then initially, the concentration of COCl2 will be equal to the mole value, which is 0.100 moles divided by the same volume, 10.0 liters. And that would be equal to 1.00 times 10 to the minus 2 m, right? So these are the initial concentrations of all the different components in the system. Now, what we need to do now is find QC. So QC would be equal to the concentration of COCl2, which is 1.00 times 10 to the minus 2, divided by 1.00 times 10 to the minus 3, multiplied by the same thing. So I'm just going to put squared here for simplicity's sake. And let's see what we have here. 1 times 10 to the minus 2, divided by 1 times 10 to the minus 3, minus squared. And that would be equal to 1.00 times 10 to the 4. All right? So what we're going to do next is compare QC to the given KC value. And which one is greater? QC is greater than KC, which means that if QC is greater than KC, that means that the reaction is going to shift to the left. All right? So if the reaction shifts to the left, what that means is that some of the COCl2 will react to form CO and Cl2. All right? So we're going to set up our ice table. So I'm just going to rewrite the equation here. CO plus Cl2 to give COCl2, right? Initially, you're going to have, according to the calculations that we have here and here, you're going to have 1.00 times 10 to the minus 3 m. Here you're going to have 1.00 times 10 to the minus 3 m. And for the COCl2, that would be 1.00 times 10 to the minus 2 m. And then we're going to have the change. The change here, because the reaction, and this is the reason why we went through all this trouble to figure out the direction of the reaction. Because the reaction is going to shift to the left, what that means is that if X represents change in concentration of CO, then basically that means that as far as CO is concerned, that will be plus X. As far as the CO2 is concerned, that will be plus X. And as far as the COCl2 is concerned, that will be minus X. All right? So that at the end of the reaction, you're going to have 1.00 times 10 to the minus 3 plus X. Here you're going to have 1.00 times 10 to the minus 3 plus X. And here you're going to have 1.00 times 10 to the minus 2 minus X. All right? So all we have to do now is plug these into the Kc expression because these are all equilibrium values. So Kc, and by the way, what Kc is equal to? Kc is equal to 1.2 times 10 to the minus 3. So 1.2 times 10 to the minus 3 would be equal to the concentration of COCl2, which is 1.00 times 10 to the minus 2 minus X, divided by 1.00 times 10 to the minus 3 plus X squared, because again, you're multiplying it this by this. So, as you can see, this is going to be another algebraic problem. So how shall we solve this? We can cross multiply. So that means that 1.2 times 10 to the minus 3 times 1.00 times 10 to the minus 3 plus X, and that is squared, will be equal to 1.00 times 10 to the minus 2 X minus X. And then, yes, ma'am.
Shouldn't the Kc value be a positive and not a negative?
Shouldn't the Kc value be what?
A positive 3? 1.2 times
Positive?
10 to the positive 3.
Oh, yes. Thank you for pointing that out. So this should be plus 3 here. So this should be plus 3 here, okay? All right, so what we're gonna do, well, first we have to work out what this is within the parentheses. So that would be 1.0, if I remember from my math days, squared. Let me do this here. I'm going to put the 1.2 times 10 to the minus 3 outside the square parentheses, and then I'm going to work out what this is equal to. This would be equal to that multiplied by itself, then that multiplied by x, and there will be 2 times that, so that would be plus 2.00 times 10 to the minus 3 plus x squared. All right. Equal to 1.00 times 10 to the minus 2 minus x. And then I'm going to multiply this distribution, basically. So let me do the calculation here. So 1 times 10 to the minus 3 squared multiplied by 1.2 times 10 to the 3. I keep making that mistake that you just corrected me on. It should be 3 here. Okay, let me do this again. So 1 times 10 to the minus, and then I square that, and then I multiply by 1.2 times 10 to the 3. So here, I'm going to get 1.2 times 10 to the minus 3 here. And then when I multiply 1.2 times 10 to the 3 by 2 times 10 to the minus 3, I'm going to get 2.4. And then here, I'm going to, and this will be, this should be x here, by the way. And then for the, and then this is just basically 1.2 times 10 to the 3 x squared. And that will be equal to 1.00 times 10 to the minus 2 minus x, all right? So bringing like terms together, what I'm going to do is minus 1.00 times 10 to the minus 2 from both sides. No, not there. That will go here. 1.00 times 10 to the minus 2. And this should be x squared, by the way. And then I would add x to both sides. So basically, this becomes 0. This becomes 1.2 times 10 to the minus 3 plus 1 times 10 to the minus 2. So according to my calculation, this gives rounded off to 2 decimal places. Okay, 0.0112. Let's leave it at that. This would give you 3.4. And then this part here will give you still 1.2 times 10 to the 3 x squared. So we have a form of a quadratic equation of x here, right? So you know the formula for the quadratic equation, which is x is equal to minus, what is it again? Minus b plus b squared. Yeah, that formula. Now, since I'm a nice person, I won't expect you guys to, use that formula, because that would, of course, especially in a test-taking situation, that would, complicate things a bit, So I know some of you have these fancy calculators. I'm not sure about these that you guys I'm seeing here, but I know you guys have calculators that you can program to solve for quadratic equations, right? All you have to do is plug in the A value, the B value, and the C value, and it gives you the 2 possible answers, right? I will allow you to use those calculators for that purpose, all right? To solve an equation like this. Now, again, being the lazy person I am, I like to use the quadratic formula calculator that's available online, which unfortunately for you guys, you won't have access to during your test. So let me see if this is the one that I use very often. Okay. So this is what I'm going to use to solve for, oops, make this a bit smaller. Okay. So for the A value, 12,000 Right, oh, by the way, let me go back to this here. So let's identify the different values. This will be the A value, this will be the B value, and this will be the C value, all right? Okay, so the A value is 1.2 times 10 to the 3, which is the same thing as 12,000. Let's select that here. The B value is going to be 3.4. And the C value is going to be 0.0112. And then I'm going to press calculate. Let's see what the answers are. So according to this, oh, something is wrong. We have two imaginary numbers. That means we made some mistake here.
I think you were supposed to, I think you added the C values together instead of subtracting.
Thank you very much. You're absolutely right, because I subtract here, I should have subtracted here. So this becomes what? 1.2 times 10 to the minus 3 minus 1 times 10 to the minus 2. So that gives you minus 88. Thank you very much for that correction. So the C value should be, whoops. The C value should be minus, and correct me if I'm wrong, but I got minus 8.8 times 10 to the minus 3, right? That's what I got. Okay, good. So let's see if that works. Going back to the calculator here. So I'm going to replace this number here with minus. So let me do this. So 8.8 times 10 to the minus 3, that will be 0.0088. And that will be minus. Okay, so let's calculate and see what that gives. And now we have two values. Now this makes sense, right? We have two values. We have x equals to this and x equals to negative that. Now, in reality, there's no such thing as a negative x value when it comes to this system. So basically what we're going to do is choose to use the positive value, which is x equals to 0.0164. So x will be equal to 0.00164. And therefore, based on that, we can determine what the question is asking for. But first we have to find out what happens when we put those numbers into this expression right here, all right? So what I'm going to do is, I'm going to do some erasure here. That, all right, let me just do erasure. I'm trying to find an easy way to do this, but I guess. Okay, I think. Oh, okay. All right, so we found out that x is equal to this, right? Let me see if I can move this up here. Okay, so this is what x is equal to, 0.00164. So basically all we have to do now to find the concentrations of each of the components at equilibrium, we can say that based on this right here and this right here, the concentration of CO is equal to the concentration of CO2, which would be equal to 1.00 times 10 to the minus 3 m plus x. X we found to be equal to 0.00164. And then the concentration of COCl2 would be equal to 1.00 times 10 to the minus 2 minus x, which is 0.00164. So let's work out what each of these give. Calculator. So 1 times 10 to the minus 3 plus 0.00164. So this gives 2.64 times 10 to the minus 3 m. And then as far as the next line below, this gives 8.63 times 10 to the minus 3 m. So the question is asking for the number of moles of CO, which would be the same thing as the moles of Cl2. That will be equal to the molarity, which is 2.64 times 10 to the minus 3 m multiplied by the volume, which is what, 10 mils, right? I mean 10 liters, right? So multiplied by 10.0 liters. So that would be 2.64 times 10 to the minus 2 moles. And then for the moles of COCl2, we take its molarity, which is 8.63. Oh, yes, ma'am.
The molarity for the COCl2, it should be 8.36 times 10 to the negative 3.
You're right. I transposed the numbers, 8.36. So this should be 8.36 here. Thank you. Times 10.0 liters, and that gives 8.36 times 10 to the minus 2 moles. So these are the answers that the question is asking. All right. So admittedly, it's a long process, and the main reason why it's long is because of the algebraic part of it, right? You have to derive the algebraic equation in this case and then solve for x. And in this case, you'd have to go the quadratic route. And that's the reason why I will allow you guys to use those fancy. I'm not sure, do these calculators, can you do that with?
These, I
Yeah.
think so. So like, so if we like do the quadratic formula, we just have to kind of do it like that.
If you can get your hands on, what's a calculator?
Is it a scientific or like a?
Yeah, I remember.
I have one of these. I need to charge it, but it's
Let me
like,
see.
it's like a graphing calculator.
I think that you can do that. You can program it, and then you put the A, B, C values, and then press execute, and then it gives you the two possible values. All right. So if you can get your hand, at least for test time, if you can get your hand on a calculator of that type. I used to see them a lot with students, because some students told me that some of their math courses require that specific.
After this, we're allowed to use it, but she said that it's not required.
Oh, okay. I remember years ago, a couple of students telling me that they require that their math. I don't remember what math course they said, but they said that their math course required the use of that calculator.
I took pre-cal trade and he did not allow graphing calculators whatsoever. We had to use these.
Oh, really?
Yeah.
Oh. Well, if you can get your hand on, at least a calculator that can do this, and because as you can see, it can get a bit tedious, and and I worked this out using the calculator online. So if you can imagine going through the trouble of, x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a, and plugging your numbers in by hand.
Yeah.
That can be a bit of a challenge, especially during test time. So if you can get your hands on a calculator where you can just program it and put the A, B, C values in and get your answers, I would definitely recommend that. All right. Okay, I think this is the last topic. Yeah, that's it. That's pretty much the end of this chapter here. Okay, let's go to the assignments. Let me go here. Let me clear this or close that. Okay, let me go here. Let me do this. And then let me go here. And go to assignments. And then go to assignment number 3. Download. Okay, so now, based on what we have covered, we should be able to do the rest of this assignment. And if I remember correctly, we completed 6, right? Did we? Okay, good. So we're going to move on to 7. Now, based on what we have done, you should be able to do this one. It gives you the equation, and it tells you that at equilibrium, they gave you the volume of the vessel, very important. They gave you the moles of HI that you're starting off with initially, and they gave you the concentration of HI at equilibrium, and you're asked to find Kc. So the first thing I would write down is the expression for Kc. So tell me, what is the expression for Kc? Based on this equation here. Kc is equal to what? Concentration of H2 times concentration of I2 divided by concentration of HI squared. Okay, so that's the first thing I would write down, right? Because what we need to do is find out what the equilibrium concentrations are, and then we plug it into that equation, right? Now, they told us, scroll back up here. They told us that the initial mole value of HI is 0.200 moles, and they gave you the volume, right? And then they gave you the concentration at equilibrium. So the first thing that would come to my mind with a question like this is the ICE table, initial, change, and equilibrium, right? So what I'm going to do is rewrite this equation. Come on. And then I'm going to set up the ICE table underneath it. So 2HI, the form H2 plus I2, and then initially, I'm going to start to, before we even do that, what am I thinking? I would find out what the initial concentration of HI is, right? So concentration of HI initially would be equal to the moles, which is 0.200 moles, divided by the volume. What was the volume? Huh? What's that?
2.00.
2.00 liters. Okay, so that gives you 0.100 M, all right? So that would go here, 0.100 M, all right? Initially, you would have no H2 and no I2, right? We don't know what the changes are yet, but what we do know is that at equilibrium, the concentration of HI is 0.078, right? M, all right? So, let me just erase this here. So, question is, what would be the change in the HI? The initial value was 0.100, and then at equilibrium, it's 0.078. So that would be what? What would be the change here? What would be the change from going from here to here? You need to fill the space right here. Sorry? Minus 0.22, exactly. Oh, 0.022, I'm sorry. All right? M, all right? So if that's a change for the HI, what say you would be the change for both the H2 and I2? Because it's a 1-to-1 ratio between the two, right? Between H2 and I2. So whatever the change for the H2 is, the change for the I2 will be the same. So what say you would be the change for the H2? Plus what?
0.022. plus 0.022.
No, you know why? You have a 2-to-1 ratio here between the HI and H2. So it would be plus half of 0.022 M. And the same would be true for the I2, plus half. You have to think of the stoichiometry of the equation. All right? So basically, the result here would be that the concentration of H2 at equilibrium is going to be half of that, which would be 0.011 M. And the same would be true for the I2, 0.011 M. All right? So therefore, now we can find out what the Kc is because we now have the equilibrium concentrations of all the different components in the system. So this is the equation that we're going to use. And therefore, Kc will be equal to 0.011 M, where we don't need the M because we don't care about units when it comes to calculating Kc. Was 0.011 squared divided by 0.078, and whatever that gives, 0.011 squared divided by 0.078, and according to my calculations, rounded off to 2 sig figs, I got 1.6 times 10 to the minus 3.
Shouldn't the box square be squared as well?
Oh, right, thank you. And
I got 0.019.
okay, so rounded off to 2 sig figs, the answer is going to be 2.0 times 10 to the minus 2. At least that's what I got. You got it? Okay. Okay, so Kc will equal to 2.0 times 10 to the minus 2. And that's how that is done. All right? Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, let me clear this if that's okay by you. Can I clear it? Okay, let me clear this. Let me close that down. Let me scroll down and see what's coming up next. Okay, so this question, now this time it's a totally gaseous system, and instead of working with Kc, we'll be now working with, at least at the beginning part, with Kp. And they gave you the equation, and they gave you the Kp, I'm sorry, not the Kp, the pressure values for SO2, Cl2, and for SO2, Cl2, right? And the first question is the above system at equilibrium? Oh, by the way, they gave you the Kp as well. This is the Kp, right? So the question is the above system at equilibrium? So how would you determine if the above system is at equilibrium?
Seeing if both sides are equal.
Nope. Hint, hint. Remember this? Right. The system will only be at equilibrium if QP is equal to KP. All right? So what we need to do is find QP. QP would be equal to, at any time, the pressure of SO2 times the pressure of Cl2 divided by the pressure of SO2 Cl2, right? And then we put the numbers in. So for the SO2, that's 0.30 times, for chlorine, that's 0.16 divided by, for SO2 Cl2, that's 0.50. And we do the number crunching, 0.3 times 0.16, and then we divide by 0.5. And according to my calculation, this is equal to 9.6 times 10 to the minus 2. Oops. Let me do this again. 0.3 times 0.16 divided by 0.5. So, which is the same thing as 0.096. All right. So we're going to compare 0.096 to 0.011. So what does that tell us? Exactly. Since QP is not equal to KP, then system is not at equilibrium. All right? So the next question is, based on that, if it is not at equilibrium, in which direction will the reaction shift or move in order to establish equilibrium? And in this case, QP is greater than KP, because QP is 0.096, KP is 0.011. So which direction you think, well, so let me write down here, QP is greater than KP, right? So if that's the case, if QP is greater than KP, which direction will the reaction shift in order to achieve equilibrium? To the right? Why do you say that? Remember, we want to get QP to be equal to KP in order for equilibrium to be achieved. If QP is 0.096 and KP is 0.011, then what must happen to the reactants or the products, or both actually? You want QP to be lowered to be equal to the KP. KP is here, right? And QP is here, right? So QP, when the system has the value for QP, it's not an equilibrium. So the question is, how do you bring the QP down to be equal to equilibrium? What must happen to the top part here, the denominator? It has to do what? Increase? Decrease, right? And this part here would have to increase. So what does that mean for this system? Which direction will it shift in order to decrease the amount of products and increase the amount of reactants? Shift to the what? To the left, exactly. So therefore, the answer for this one here would be the system will shift to the left. Because by shifting to the left, the concentration of the reactants will decrease, the concentration of the products will increase, and therefore QP will be lowered to be equal to KP. All right? Okay. Any questions so far? Questions? All right. Can I clear this? All right, let me clear this. Let me do this. And let's scroll down some more. Okay. So the question now becomes, what will the concentration of SO2, and I don't think we'll have time to do this one here. I think that's the last question. Oh, no, there's one more. Okay. What will the concentration of SO2 when the system achieves equilibrium? Let me give you like, let me start you off. So again, you have to do an ice-stable thingy. So let me, so the equation is, okay, so it's the SO2 undergoing decomposition. So, okay, so the equation is SO2, CO2 to give SO2 plus CO2, all right? Now, I don't want to scroll back up and down. Can you tell me what the initial, did they give the initial concentration, right? What are the initial concentrations? Firstly, for the SO2, CO2, help me out here.
It's pressure.
I'm sorry?
Pressure.
I mean pressure, I'm sorry.
Oh, okay, sorry.
Okay.
So 0.5018.
0.50,
50.
okay. What about SO2? Hmm?
0.30.
0.30, and chlorine?
16.
0.16, okay. So these would be the initial values, right? Now, because we know that the reaction is going to shift to the left in order to achieve equilibrium, we can say that as far as the changes are concerned, for SO2 and CO2, they will be minus X because of the 1-to-1 mole ratio between those two. And then here you're gonna have plus X, right? So at equilibrium, you're gonna have 0.50 plus X. Here you're going to have 0.30 minus X, and here you're gonna have 0.16 minus X. And then we write down the Kp expression. Kp would be equal to the pressure of SO2 times the pressure of chlorine divided by the pressure of SO2 CO2, CO2. And then we put the terms in. We're gonna have 0.30 minus X multiplied by 0.16 minus X, and then divide by 0.50 plus X, all right? And then this will be equal to Kp. What's the Kp value? Can somebody help me out here?
0.011.
0.011, right? And that's basically what you need to solve, which we won't have time to do today, but I can continue with this next class. No, next class is your test, so the next class. All right? But you can try this on your own. If you have any problems, feel free to talk to me during my office hours. All right? So I'm going to stop here for today. So let me remind you, your test on Thursday, on Wednesday, will be based on solutions, colligative properties, osmotic pressure, 1-point elevation, freezing point depression, what's the other one? Vapor pressure lowering, calculation of molality and all that. And then the next chapter is kinetics, right? So all that's involved in kinetics, rate laws. You can rest assured that you'll be getting at least one question where you're going to get to determine the orders of reactions of different substances involved. Where you get a table and then you go through the steps. Half-lives, you need to remember the half-lives equation. You need to remember the integrated rate law equations. And what else? Arrhenius equation. You need to understand how catalyst works, which means that you need to understand the activation energy. I'm just trying to remember the different topics. But those are the topics that come to mind right now. So, like I think I told you guys, make sure you review your assignments, review the assignment keys. I think I've posted some past test questions. So review that as well and try to do as many questions from your textbook as possible. And I'm available for office hours if you need help. Well, I'll be in my office today from 2 to 3. Unfortunately, I won't be available tomorrow because our class is pretty much all day. In fact, I think I might be hanging out here later on. I don't know yet. Depends on how I feel. But I do have office hours from 2 to 3. So if you need help during that time, please feel free to give me a call or come by my office, all right? Okay, so that's it, folks. I'll see you guys on Wednesday. What's up? Okay, so this is the equation. So delta N will be 2 minus 3, so that's minus 1. No, but it should be plus 1. It should be, remember, it's products. It's the sum of the coefficient of the products minus the sum of the coefficient of the reaction. So this should be the other way around. So this should be 2 minus 3, which will be minus 1, and then that makes it positive 1. Yeah. Remember, it's a number of.
So then this would be, so this one is correct. So I did this one. It's 5
Yeah,
Okay.
exactly.
So
Right. Yeah. Remember, it's the sum of the coefficients of the products minus the sum of the coefficient of the reactant. Yes, sir.
How many questions around this?
About 3, at least 3. In fact, I don't see more than 3 questions.
Okay, one more is gonna be the order reaction.
I'm sorry?
One of them is gonna be the.
Yeah, one of them definitely would be, that table that I gave you guys. One of them is like that. Yeah.
Thank you.
Mhm.
So then I would just do 5 - 9, which would be -4, but since there's a negative sign at the end, it'd be +4.
Exactly. Just think, it's always products minus reactant, products minus reactant.
And
Okay,
then we're just only supposed to be studying exam, assignment 1 and 2.
yeah, assignment 1 and 2, solutions and then kinetics, and that's it. So like what we did today, it won't be on the test.
So assignment 3 won't be on it.
Huh?
This is,
Assignment 3, no, won't be on it. That's for the next test.
yeah,
Yes, ma'am.